10.3 deals with a mathematical word that I actually think is kind of funny. The word is modeling. When I think of the word modeling, I do not think of math at all. I think of people wearing weird, fashionable stuff on a runway and tripping and falling sometimes. And people recording and saying, "Did you see the models fall down?" Oh. As a matter of fact, I have a video I'll show you guys later in fourth period, just for you. Not the people at home, but just for you. Just see if you think it's funny too, because I see a funny video in my head. Anyhow, modeling in math actually deals with real world problems that model what we're doing with quadratics. So math teachers love to talk about how when you shoot something up into the air, it follows the shape of a parabola. That is, when an object is floating through the air, either it's thrown there or shot there or whatever, but if it's moving through the air and it doesn't have anything on it, like wings or like a baseball being thrown by a pitcher, or a golf ball that's being hit by a golf club, things that are being affected by nothing other than gravity, they all are affected. It doesn't matter if it's like this or if it's like this. They take on the shape of a parabola. That's because the acceleration of gravity causes something to increase and then decrease. Think about it. Like, that's why we're learning it. We can actually figure out lots of different things. So everything on 10.3 deals with word problems that actually have this math involved in them. The biggest hints I can give you before you do the worksheet: pay attention to what you're measuring. The equations a lot of times will tell you this x measures blank. It could be seconds, it could be money, it could be price, it could be cost, it could be how many widgets. I don't know. They will tell you what the variables are measuring. That will help you figure out what goes on your horizontal axis and what goes on your vertical axis, your domain, and your range. I also want to remind you that you can choose the scale of what you want to count by. Thank you. If you're making an axis and you're counting by, and you know that the vertex's highest point is in the hundreds, don't count by ones. That'd be a long way to count. Count by 20s. 20, 40, 60, 80, 100. Yay, I'm there. Count by 50s. 50, 100. I'm there. You know what I mean? Keep in mind, you can choose to count by whatever you want to, as long as they're the same increments. Sometimes you might use tens, hundreds, or even thousands if it makes sense. If you have to go to 8,000, count by 1,000. Count by 2,000. Make it easy on yourself. Lastly, I think there's a typo on your worksheet that I just passed out to you. Most likely there is. If you look your number at number 1, I'm hoping that your number 1 worksheet says negative 16 x minus 2 squared plus 64. If it does not say that, please cross off your equation and write down the correct equation. I'll zoom in on it so you can see the correct equation. Now there's only 6 questions on this worksheet. I cannot do every single question with you, but I can do the first question, all A through J parts we could do together. If you want to do this worksheet with me or on your actual worksheet, that is totally fine by me. Here we go. A golfer hits a ball from the fairway to the green. The flight of the ball is modeled by this equation, where x, let's underline this, where x is, what is it? It's the time in seconds since the ball was hit. And g of x is, is the height of the ball in feet. Those two things are going to let us know what our equation is doing and what its values are. So here we go. Add labels to the axes, including the variable, description, words, and units. So they're asking you, what does this horizontal axis need to measure? When you go over here and you know that your x measures time in seconds. Technically, this is time, but our units should be seconds, so I'm going to put that in parentheses. Our y-axis is also known as this part, the g of x part of the function. This is the same thing as y equals. The y is the height of the ball in feet. So I'm going to call this the height, and it's measuring in feet. I'll put that in parentheses. I would not know that unless I read the rest of the equation. Like, you got to read the sentences, okay? I have done part A. Part B, focus on the equation used to model the ball's flight. What will the graph look like? Be as specific as possible. Now we're looking at the equation. It has a negative a value. It's going to open down. The a value is 16. Ooh, that's going to be super skinny, or it's going to be narrow. Do you know where your vertex is? Do you know opposite same? Is this vertex form? Yes, opposite same. 264 is going to be the vertex. So right now, based off of those three things, I kind of have an idea of what it's going to look like. Scale each axis so all important features of the graph will show. Well, is this going to be the maximum point? Is it going to be the highest point? Is it going to go up to how high? It's going to go up to 64 feet. How long is it going to take?
Oh, I would say it's not the same equation.
What did she miss?
Oh, wait.
Somebody tell her.
Oh, I'm sorry.
It's okay. You missed something, but it's all good.
Okay.
So this is the y-coordinate of the highest point. This is your x-coordinate. Now look what this is measuring. This 2 means that it's going to take you how long to get up to a height of this. It's going to take you 2 seconds to reach a height of 64 feet. You know that. Like, that's what this represents. So we're going to scale this. If I got to go and do 2 seconds, here's what I'm going to do. I'm going to say that this is 1, 2 seconds, 3 seconds, 4 seconds. I could even go more, but I'm going to put 5 seconds there. I'm scaling it. That's what you're counting by. I need to get to 64 feet. I'm not going to count by ones. That's no way. I'm not going to count by fives. That's too small as well. Tens maybe? 10, 20, 30, 40, 50, 60. I'll put a 70 in there just to go a little bit further. Maybe I should have counted by 20s. I don't know. But there you go. That's what this is. Scale each axis. I pick whatever I want to count by. Make sure they're in equal increments. Your math teachers like that. I'm supposed to graph the parabola. So if you know that this is the vertex, I can go to 2 seconds and then go up to 64 feet, and I can put a dot somewhere where I think 64 feet is, right about, well, what am I doing? Let me press the button. Oh, there we go. 264 feet. Right about there. There's my parabola. No, that's not a parabola. That's just my first point. 16. It's going to go down by a lot of feet, right? Like, how far is 16 feet from here? 64, 16 feet. From 64 is 48. Is that right? 48? Yeah, I think it is. I should be going, for 1 second, I should be at 48 feet. One second, 48 feet. Now, some of you might wonder, like, what are you doing? So I'm just making a parabola. I'm sort of sketching it at this point because there are some key points that I don't know. If I want to know where this is at 0 seconds, what I can do is I can plug in 0 into this equation. Watch. Negative 16 times 0 minus 2 squared plus 64. I can actually figure out where is this golf ball at 0 seconds. 0 minus 2 is negative 2. Negative 2 times 2, or squared, is negative 2 times negative 2 is 4. 4 times negative 16 is negative 64 plus 64. The height is 0. So I know my parabola has to go through 0, 0. See ya. Good luck. I'll see you in a bit. Adios. If it travels all the way to its highest point and takes 2 seconds, I bet you that at 4 seconds, it hits the ground. I bet you if I plugged in 4 minus 2 squared, I would get the same answer, and I would get that it is 0 feet off the ground. But basically, I have a parabola. That's what I'm trying to graph right there. I'm just trying to graph it and make sure the scale is right. Why does it make sense that this graph is only in the first quadrant? Is the ball going to move up or over when it's not being hit? Does the height change at all before it gets hit by the golf club? It doesn't move at all. So why are we doing it? Because we're only using, it makes sense to use this because this is where the height changes, right? Luke, you're supposed to take this before you leave. Thank you. See ya. Why does it make sense to graph only the first quadrant? Because the height only changes from 0 to 4 seconds. That's what I'm going to say. I would accept some other answers there, but at this point, nothing's happening before it. You can't use negative values at time. That doesn't make sense. It doesn't make sense that the height is ever going to go below 0. Oh, it went negative 100 feet. What? Okay, I know parabolas go forever, but it doesn't make sense that it's going to just keep falling, right? It has to stop sometime. It doesn't go through the earth. It doesn't make sense to me, you know? Okay. Using the graph. Identify domain and range. I think our domain, I know we normally talked about all reals, but look at this graph. In real life, we're only using values from 0 up through 4. That's our x. Our x is between 0 and 4. We're not using all reals this time because we're only using x values from 0 to 4 seconds. Now our y values, are we using all y values? Are we using all y values less? No, we're using y values that are here up to here. We only have y values that are from 0 feet all the way to 64 feet. 0 is less than y is less than 64. These values are what make sense to me in real life. Part F. What is the maximum height of the ball? I bet you guys know that answer. What is it? Say it out loud if you know it. I agree. 64 feet. How do you know? It's the vertex. It's the highest point. Vertex is the maximum. Vertex is the maximum point. Doesn't get higher than that than the vertex. That y value is the highest point. Now I like this question part H, and you should get used to being able to do part H. It says, how high is the ball after 3 seconds? You could try to guess based off of this graph, but it's just easier to take this equation and plug in 3. Negative 16 times 3 minus 2 squared plus 64. Let's write that down. Let's plug in negative 16 times 3 minus 2 squared plus 64. This will tell us how high is the ball after 3 seconds. In parentheses first, exponent second. 1 times 1. Negative 16 plus 64. There's that 48 feet again. 48 feet after 3 seconds. Challenge. How long is the ball in the air? It's not much of a challenge because I helped you figure that out. The challenge will be what happens, how long is the ball in the air when you don't have a graph that we've figured out. That'll be the challenge. How long is the ball in the air? If you know, say it out loud. I agree. I want to just give you a hint because I know that there will be some problems like this in a later review and toward the end of the review. If I really want to know this, I'm trying to figure out the time. I could set 0 equals negative 16x minus, what was it, 2 squared plus 64. If you put in that the height is 0, then you can figure out at what time in seconds will the height be 0. There's a way to figure that out. This is going to open up the door for you to do all those kind of problems. Okay, but that's a future question, not this one. 4 seconds, the ball's in the air. How do we know? Did you use the graph? Did we plug it in? I'm just going to say we used the graph. Okay, so we did the whole first page. They're not all this detailed, but I wanted to walk you through at least one of these so that you can do the rest hopefully on your own. I'm going to stop your notes right there.